Welcome to the 24th lecture of the MOOC on parallel algorithms. From today's lecture, we will start a study of the interconnection network algorithms. We have already seen an introduction to the interconnection networks, and we have seen some algorithms on them. Today, we begin a detailed study of this idea. So, we will begin with linear arrays. You would recall that in a linear array we have a number of processors connected up in this manner. Every intermediate processor has got two neighbors, one on either side, but the processors at the extremes have got only one neighbor each. The extreme processors have a degree of 1, every other processor has a degree of 2. So, such an arrangement of the processors is called a linear array. We saw an algorithm for sorting on the linear array. Let us recapitulate this algorithm and do an analysis of this, which we hadn't done earlier. This was called the odd even transposition sort. So, let us take an example. So, let us say we are given a linear array which holds these elements, which are to be sorted in place. What this means is that the processors already hold these elements. These elements are not streaming into the linear array. The linear array is already filled with these elements, and what we need to do is to sort them in place. So, the algorithm groups them from the left. An odd element is paired with the even element coming next to it. So, 6 is paired with 4, 7 is paired with 3, and so on. That is because the first position and the second position form a pair, third position and the fourth position form a pair, and so on. And then for each pair we perform a compare and exchange. When 6 and 4 are compared, we find that 4 is smaller than 6, so we exchange them. Here we have 3 smaller than 7, we exchange them. 1 is smaller than 8, there is nothing to do. 2 is smaller than 5, there is nothing to do again. Then in the next step, we pair every even element with the subsequent odd element, which means 6 is paired with 3, 7 is paired with 1, 8 is paired with 2. We compare and exchange. 4 remains where it is. Here we have 6 3 rectified to 3 6, 7 1 becomes 1 7, we have 2 8 and 5. Then we go back to the original pairing, the odd even pairing. Here we have 3 and 4, 1 and 6, 2 and 7, 5 and 8. And then once again we have an even odd pairing. Again we have an odd even pairing. And the next even odd pairing will fix the array. So, we find that the solution emerges after a number of steps. But what is a number of steps? Let us find out how many steps are needed to sort n items on a linear array of n processors. To prove this, we shall fall back on a principle that we have already seen, which is called the ZeroOne principle. You will recall from our algorithm on comparative networks that ZeroOne principle can be used to to prove the correctness of sorting algorithms. What ZeroOne principle says is that if an algorithm A sorts correctly every binary sequence, then it sorts correctly any sequence drawn from a linearly ordered set. So, to prove that our algorithm works correctly, it is enough to show that it works correctly on all binary sequences. Then by the ZeroOne principle, we can argue that it will work correctly on any single input. So, let us see what happens to a ZeroOne sequence when it is subjected to the odd-even transposition sort. Let us take a binary sequence, we pair them off in this fashion, odd even, odd even, odd even, odd even, and then we sort them. 1 0 becomes 0 1, and then we pair them even odd, again we pair them odd even, you find that the algorithm now begins to converge. At the next iteration, we have all the zeros at the left end and all the ones at the right end. That is, when a binary sequence is sorted, we will have an arrangement of this form. If the sequence has L zeros and n minus L ones, then at the end of sorting, all the zeros will be at the left extreme and all the ones will be at the right extreme. So, let us now try to argue that when odd-even transposition sort is applied on a binary sequence, it will terminate within some number of steps. In particular, let us consider the rightmost one in the sequence. Let us look at the example here. Here this happens to be the rightmost one. Here the rightmost one is compared with the 0 on its right and therefore gets exchanged for the 0, and therefore it moves to the second position in the second step. And then it further moves on to the next position in the third step, and in the fourth step it has reached its final destination. So, what we find is that once the rightmost one starts moving, it will keep moving. This is because the rightmost one is going to encounter all zeros to its right. So, whenever it pairs with an element onto its right, it will get exchanged with the element. So, it is moving on to the next position. In the next step, we will have a different kind of pairing. This one will be paired with the 0 further to its right. Therefore, it will move once again. and once there it will the pairing changes again, and therefore it will be paired with the 0 further to its right, and so on. Therefore, what we find is that once the rightmost one starts moving, it will keep moving. But then when will it start moving? In our example, we find that the rightmost one is at an odd position, and therefore it is paired with an even element to its right, which happens to be 0. Therefore, the one will start moving in the first step itself. But this need not be the case always. When we take a sequence of this form, here the rightmost one is this one, the circled one, and that is paired with a 1 on the left side. Therefore, in the first step, it will be compared with the 1 on the left side, and this will ensure that the element does not move. So, it is possible that this element does not move in the first step. But if the element does not move in the first step, it will certainly move in the second step, because in the second step it is paired with the subsequent 0 which is to its right. And then there will be an exchange, this becomes 0 1, and then this 1 will be paired with the next 0 in the next step, and it will keep moving to the right. So, what we find is that the rightmost one will start moving either in the first step or in the second step. That is, if the rightmost one fails to move in the first step, we know that it will certainly move in the second step. And once it starts moving, it will keep moving. Now, what is the final destination of the rightmost one? It is supposed to go and occupy the nth processor. So, its destination is n. And where does it begin the journey? The rightmost one could be the first element. If there is only one 1 in the sequence, and that happens to be the leftmost position, so the worst possible source for the rightmost one is 1, which means the rightmost one has to travel a distance of at most n minus 1. In the worst case, it starts from position 1 and has to reach position n, therefore, it has to travel a distance of n minus 1. And again, in the worst case, it might not start moving in the first step. So, in any case, we can say that by step n, it reaches the destination. Of course, the analysis could be tighter, but for our purpose we can say that the element will reach the destination by the nth step. Now, let us come to the second rightmost one. It could be that the second rightmost one is paired with the rightmost one in the first step, and therefore, it does not move, nor does the rightmost one move. In the next step, this is paired with an element to its left, and therefore, does not change, and the rightmost one will now change. So, the rightmost one has now moved after the second step. Now, the second rightmost one will be paired with the 0 which appears to its right, and therefore, it will start moving. So, in this case, we find that the second rightmost one starts moving in the second step, but then it is possible that it does not move in the first step in the second step even. Yeah, the second rightmost one could be blocked by the rightmost one in step 1. That is, the second rightmost one and the rightmost one are paired in the first step. So, they fail to move, neither of them moves. Then let us say in the next step it is paired to the left, and therefore, it does not move again. This could be either 1 or 0. So, it does not matter. The second rightmost one fails to move in the second step also, but in the third step, now the rightmost one has moved away and a 0 has appeared in its place. Therefore, the second rightmost one will get paired with that. Therefore, this will now start moving. Now, in the third step, the second rightmost one will start moving. By this time, the rightmost one has moved away, and therefore, there are zeros between the second rightmost one and the rightmost one. Therefore, what we establish is that the second rightmost one will start moving by the third step and will keep moving afterwards. Now, the destination of the second rightmost one is processor number n minus 1, and its worst case source is 1. Therefore, it has to cover a distance of at most n minus 2. Now, what we have established is that it will start moving from the third step, that is latest by the third step, therefore, what we know is that even the second rightmost one reaches its destination in step n or earlier. So, you can repeat this argument for the other positions. In general, you can consider the ith rightmost one. You can show that this will start moving by the I plus first step, and the destination for this is n minus I plus 1. Therefore, the ith rightmost one reaches the destination by the n step. So, what we have established is that every one reaches the destination by the n step. Then by that point in time, all the zeros will be to the left of all the ones, therefore, the input will be sorted. So, what we have established is that the odd even transposition sort runs in n steps. So, it is possible to sort n elements on a linear array in n steps. So, now let us escalate to the higher model. The next model that we consider is the two-dimensional mesh. Let us say on a two-dimensional mesh, we want to sort the elements in snake-like order, which is this order. We have seen an algorithm for this already. Let us once again do a recapitulation of this algorithm. Let us say we are given this mesh, so we are given this array, two-dimensional array. What we do is to sort the rows in opposite orders. The odd rows will be sorted from the left to right, and the even rows will be sorted from the right to the left. So, here in the first row we have 3, 5, 7, 11. In the second row we have 2, 10, 12 and 15. In the third row 4, 9, 13, 16. This is from the left to the right. And then we have 1, 6, 8 and 14 from the right to the left. And then in the second step, we sort the columns from top to bottom. So, from the first column we get 3, 4, 14, 15. In the second column we get 5, 8, 9 and 12. In the third column we have 6, 7, 10 and 13. In the fourth column we have 1, 2, 11 and 16. And then once again we sort the rows. When the rows are sorted, we have 1, 3, 5, 6 in the first row, 2, 4, 7, 8 in the second row. The second row is sorted from the right to the left. This is how the mesh looks like after the horizontal sorting of the second step. Then in the vertical sorting part of the second step, the columns are sorted. The first column is already sorted, and so is the second column. The third column needs fixing, and so does the fourth column. And then we come to the third step. In the third step, we sort the rows again. So, the first row gives us 1, 2, 3, 4 in sorted order, and then the second row sorted from the right to the left will give us 5, 6, 7, 8 from the right to the left, then 9, 10, 11, 12 and 13, 14, 15 and 16. Now, we find that the elements are in sorted order. This algorithm is called the shear sort. But then, given the specification of the algorithm, it is not clear why it should terminate, and it is not even clear for how long the algorithm has to be run. So, let us now prove the correctness as well as the time complexity of this algorithm. So, once again we will invoke the ZeroOne principle. Once we invoke the ZeroOne principle, all we have to show is that shear sort works correctly on any binary sequence. And even the analysis we need to do only on binary sequences, because if the algorithm works correctly on binary sequences of with the time complexity of T of n, then it will work correctly on any linearly ordered set in the same time complexity. So, let us see how this will work on a binary input. When we sort the rows, we get 0 followed by 3 ones. This is being sorted from the left to the right. Then in the second row, we have again 0 followed by 3 ones. In the third row, it is all ones anyway, so it is already sorted. Then we have 2 zeros followed by 2 ones. And then when we sort the columns, we have The columns are all sorted from the top to the bottom. So, now in each column we find that all the zeros are at the top and all the ones are at the bottom. And then once again we sort the rows. The second row is already sorted. So are the third row and the fourth row. Then once again we sort the columns, only the last column needs fixing. We find that the sequence is already sorted. So, let us see how the algorithm behaves on a general sequence, a general binary sequence. So, we will take a root n by root n mesh. On a 0-1 sequence. We want to show that shear sort works correctly on a root n by root n mesh on which we are given a 0-1 sequence of length n. So, the elements are distributed arbitrarily over the processors of the mesh. So, at the beginning of any intermediate iteration, we can divide the rows of the mesh into 3 groups. At the top of the mesh, we have rows that are filled with all 0 rows. An all 0 row is one in which every element is a 0. At the bottom, we have all 1 rows. And in between, we have rows containing both zeros and ones. We will call the top band clean, and similarly the bottom band is also clean, but the middle band we say is dirty. So, a clean row is one in which every element is the same, either all are 0 or all are 1. So, we assume we have a clean band at the bottom as well as at the top, and in the middle we have a dirty band. A row is dirty if it has both zeros and ones. So, of course, in the beginning the clean bands could be of size 0. Initially, there could be no clean row at all. It is possible that there is not a single clean row to begin with. Therefore, the size of the clean band and the clean band at the top as well as at the bottom could be 0. What it means is that the initial size of the dirty band is less than or equal to root n initially. That is, we do not make any assumption that we have clean rows at the beginning. It is possible that every single row is dirty. So, the size of the dirty band could be root n in the worst case to begin with. Then let us see what the algorithm does. In the first iteration, or in general in any ith iteration, in the ith iteration, in the first step of the iteration we sort the rows. The odd rows are sorted from the left to the right, the even rows are sorted from the right to the left. Then when we come to the second step, we sort the columns. Now, let us consider a column here. In the column, we have a clean portion at the top, which comes from the clean band at the top. All its elements are 0. That is because in the top clean band every single element is 0. Similarly, at the bottom we have a clean band, every element of which is 1. Therefore, when the column is being sorted, there will be no change to these elements. In any case, the zeros are supposed to be above the ones. Therefore, when a column is sorted, the elements which are in its clean positions, we assume do not change their positions. So, only the dirty band elements will get sorted. Now, let us assume that the sorting is done using a different algorithm. As a thought exercise, let us assume that the columns are not sorted using the odd even transposition sort, but a different algorithm. Which I will describe in a moment. So, if the columns were to be sorted using a different algorithm, and if this different algorithm happens to be the following: mind you, this is only a thought exercise. So, we are now invoking a different algorithm for sorting the columns. What this does is the following: it pairs off the dirty rows. So, let us see what sort of scenarios can happen when we pair off dirty rows. Let us consider two dirty rows of size 4 each. Now, these dirty rows are already sorted and they are sorted in different directions for odd rows and even rows. So, when we pair them off, we pair adjacent rows together. Therefore, when we consider the next row, the pair of this row, it would be of this sort. So, let us perform a column wise compare and exchange between these two rows. So, this is a pair of dirty rows that are adjacent to each other. They are sorted from the left to the right for the odd rows and the right to the left for the even rows. So, I have done an odd even pairing. So, this is an odd row and this is an even row. It could well have been the other way. When we look at the dirty band, we take the first row and the second row and pair them off together. If the first row happens to be an odd row of the matrix, then we will get an arrangement like this. If the first row happens to be an even row of the matrix, then we will have a different arrangement. It will be just a mirror image of this, that is an upside down image of this. Now, when we sort these two rows individually, that is we sort them in isolation, then for each column when we perform a compare exchange, what we get is this. We perform a compare exchange within each column, but restricting ourselves to within the pairs. So, within these pairs we have such compare and exchanges. What we find is that one of the rows turns completely clean. So, in this case we have more zeros than ones, therefore, we get one clean row of zeros. On the other hand, if we had an arrangement of this sort, when we compare and exchange within the columns, we will get a clean row of ones and one dirty row. If the number of zeros and number of ones were exactly the same, then after I perform a compare and exchange, I would get two clean rows. So, in the different algorithm for sorting vertically column wise, what we do is this: we pair off the dirty rows adjacent rows are paired into one group, and within each group we perform a compare exchange within the columns. As a result, we will get at least one clean row out of every pair. So, what we know is that every pair gives us at least one clean row. And then let us move a clean row of zeros all the way to the top clean band. That is, in the matrix we have a clean band at the top which is all zeros, a clean band at the bottom which is all ones, and in the middle we have the dirty band. In the dirty band now we have got a row which contains all zeros. So, this is a clean row within the dirty band. Let us say we move this clean row to the top by pulling all the elements above these zeros by one position down. So, if we had two ones above, we will now come to this arrangement 0 1 1. Those two ones are pulled below the 0. If we had a 0 1 above this, we will pull them down and the 0 will go up. So, in this fashion, if we push the clean row all the way to the top, we find that every single column still continues to be sorted. All that has happened is that these zeros have bubbled to the top. One single 0 in every column has bubbled to the top. So, the columns have compressed by one single position. So, the columns continue to be sorted. This we did for one single clean row, but when we paired off the dirty rows and compared and exchanged within each pair, we got one clean row from every single pair. Now, let us do the same action for every single clean row. Every single clean 0 rows will be moved to the top and every single clean 1 row will be moved to the bottom. Then what remains in the middle will be the dirty rows. By the same argument, we show that the columns will continue to be sorted when we do this. But then this establishes that the number of dirty rows reduces by a factor of 2. If we had x dirty rows before, we have ceiling of x by 2 dirty rows now. But then we have used not the odd even transposition sort as shear sort is supposed to use, but we have used a different sorting algorithm. But does it matter? This was the result of applying some sorting algorithm, but every correct sorting algorithm should produce the same output. Therefore, in the second step of our iteration, instead of using this different sorting algorithm, if we had used shear sort, we would get exactly the same result. That is, even shear sort would ensure that the number of dirty rows reduces by a factor of 2 at the end of the iteration. So, each iteration reduces the number of dirty rows by a factor of 2. We start with root n dirty rows. So, the algorithm would require log root n iterations to reduce the dirty rows to 1. The number of dirty rows to be reduced to 1 will require log root n iterations, and each iteration takes 2n steps. If we use odd even transposition sort, that is, we use odd even transposition sort horizontally in the first step of the iteration. In the second step of the iteration, we use odd even transposition sort vertically. So, the total time taken would be 2 root n steps. Therefore, the overall time complexity of the algorithm would be 2 root n times ceiling of log root n, plus we will require one round of horizontal odd even transposition sort. So, this we can show is less than or equal to root n times log n plus 1. Therefore, this is the time complexity of the shear sort algorithm. What we have established is that when we begin with root n dirty rows in the begin with, that is the worst possible in any case. If we begin with root n dirty rows, then after so many iterations, the number of dirty rows will be 1. Therefore, one extra odd even transposition sort done over the rows will ensure that the mesh is completely sorted. So, the algorithm runs in square root of n times log n plus 1 steps to sort n elements. What is the cost of the algorithm then? We have n processors. So, n power 3 by 2 times log n plus 1 is the cost of the algorithm, which is surely suboptimal, because the sequential time complexity of the problem is order of n log n. But then the model that we use is the 2-dimensional mesh. In this mesh, each processor has at most 4 neighbors. This is the case with an interior processor. A processor along the edge will have 3 neighbors, along the top edge will have 3 neighbors, and a corner processor will have only 2 neighbors. That is, the degree of a vertex is 2, 3 or 4. What this means is that a processor is capable of communicating with only a small number of peers in every single step. Therefore, we would expect that an algorithm that runs on a 2-dimensional mesh will be considerably slower than an algorithm that runs on PRAMs. This is because in PRAMs, the presence of a shared memory allows for a rich design of communications in every single step, whereas in the case of a 2-dimensional mesh, a processor can communicate with at most 4 other processors in any single step. So, that is a tough constraint. Therefore, that makes designing algorithms on 2D mesh a lot more challenging. We certainly cannot achieve polylogarithmic time bounds on 2-dimensional meshes. Now, let us see a lower bound for sorting on 2-dimensional meshes. A trivial lower bound is 2 root n minus 2. Why is this? Let us consider a root n by root n mesh. And we want to sort n items which are preloaded into the mesh, one element per processor using the mesh. So, let us say the item that we place in the top left corner is the item which is destined to the bottom right corner. That is, we place an element x here. If we manage to sort the elements in snake like order, as we did in the case of a shear sort, then let us say x should end up in the bottom right corner. Then during the algorithm, this element will have to travel from the top left corner to the bottom right corner. Now, what is the distance from the top left corner to the bottom right corner? There are multiple paths, but let us take one single path. All paths have the same length. So, the length of this path, you find that is, you can decompose this into two paths. You start from the top left corner and come to the bottom left corner. The distance for that is root n minus 1, coming directly downwards. There are root n nodes in the mesh along this edge. So, starting from the first processor, reaching the root nth processor will require traveling a distance of root n minus 1. So, the element x has to traverse this distance, and then it has to traverse an additional distance of root n minus 1, traveling along the horizontal edge. So, the distance is 2 root n minus 2. Of course, this need not be the only path that x can take. For example, x can take a path of this sort, but then we know that the total horizontal distance has to be root n minus 1, and the total vertical distance it traverses must also be root n minus 1, because it is not possible for an element to move along the diagonal. Therefore, element x will necessarily have to traverse a distance of 2 root n minus 2, and therefore, that is a lower bound. So, in any case, you do not expect to sort in smaller root n time. Sorting is going to take omega root n time. Omega root n is a lower bound for sorting n elements on a root n by root n mesh. But let us try to get a tighter lower bound. What we are going to show is that we require 3 root n plus smaller root n steps at least. We cannot do better than this, is what we want to show. To prove this, we consider the root n by root n mesh. In this root n by root n mesh, we isolate a corner of size 2 power root of root n, 2 times root of root n and 2 times root of root n. That is, we identify a corner of this sort. In particular, in a 2-dimensional mesh, when I identify a corner like this, the number of processors in this would be, if I have taken y elements here, then that will be y into y plus 1 divided by 2. So, if y equals twice square root of root n, which is twice n power 1 by 4, then twice n power 1 by 4 into twice n power 1 by 4 plus 1 divided by 2 is approximately 2 root n. Let us say this quantity is k. This is approximately 2 root n. So, there are k processes within this triangle, and in the remaining we have n minus k processes. Now, this is an adversarial argument. You have found a fast algorithm for sorting on a 2-dimensional mesh. I want to make your algorithm do badly. For the purpose of making your algorithm do badly, I am going to cook up an input. I will cook up an input in this fashion. I will place the elements 1 to n minus k in this part. In this part, I will place the numbers 1 to n minus k anyhow. It does not really matter how they are distributed. And then the elements I am going to place in this top triangle, which has k processors, are all unknown at the moment. I will fix them later. So, at the moment they are all unknown. Then what I do is this: I take your algorithm A is your algorithm, I run A on this input, and stop the algorithm after 2 root n minus 2 n power 1 by 4 minus 3 steps. I will stop the algorithm after these many steps. Now, let us look at the mesh. This is a root n by root n mesh. Here I have identified 2 power n by 2 into n power 1 by 4 processors in the first column. Let me consider the last of these processors, the lowest of these processors. The distance from this processor to the bottom right corner is going to be root n minus 1 horizontally plus root n minus 1 minus 2 n power 1 by 4 vertically. So, this is 2 root n minus 2 n power 1 by 4 minus 2. So, the step number that I have chosen for stopping your algorithm is 1 less than this. So, I have stopped your algorithm on this input after running it for 2 root n minus 2 n power 1 by 4 minus 3 steps. So, the algorithm is now stopped. Let us look at the bottom right corner. The element which appears here is, let us say, element x. Let me call this element x. Now, based on this element x, I will choose the contents for the top left triangle. What we know is that this element x, the identity of x is independent of the unknown elements. That is because a message from the unknown elements could not have reached the bottom right corner within so many steps. The distance from here to from the shaded portion, this is the shaded portion, let us say, the unknown elements. The distance from the unknown elements to the bottom right corner is 2 root n minus 2 n power 1 by 4 minus 2, and we have spent one less step than this, one fewer step than this. Therefore, it is not possible for us to have taken any information from the unknown elements to the bottom right corner. What it means is that the identity of x is independent of the unknown elements. So, even if we change the unknown elements and rerun the algorithm for exactly these many steps, x would still end up exactly at this place, that is the bottom right corner. Now, what I am going to do is this: replace the unknown elements with m zeros and k minus m n's. Then when you run the algorithm A on this input again, If we stop the algorithm after exactly these many steps, x would be exactly where it is now, it will be in the bottom right corner. But then if you continue executing the algorithm, x would move from this position. That is because now the unknown elements are going to influence this x. So, let me define C m of x, C m x, C of m x as the column number where x ends up when the shaded portion, which is the set of unknown elements now, has exactly m zeros. With the rest being all n's. So, the remaining are all larger than the elements that we place in the unshaded portion. We have put m zeros in the shaded portion along with these largest elements. Then these m, the value of m will decide where x will end up finally. So, vary m, C m x will vary. In particular, when I vary m by 1, C m x will vary by 1. So, if I continue doing this, so if I continue varying m, C m x will attain every value in 1 to root n, in fact twice, because the total size of the shaded portion is greater than 2 root n. By varying m, I can make sure that C m x will attain every value in the range 1 to root n. This will happen in fact more than twice, at least twice. All we need is one particular value. All we need is one particular value. Suppose m prime is one value. Suppose m prime is the value that causes C m prime x to be 1. So, if I put m prime zeros in the top left corner, then the element x which appears at the bottom right corner at the end of these many steps will have to travel all the way to the first column. What it means is that the total number of steps taken is in other words, we are going to take 3 root n minus smaller root n steps for sure in sorting the elements. So, this is a tighter lower bound than the one we saw earlier. In the next class, we will see an algorithm which almost matches this lower bound. So, that is it from this lecture. Hope to see you in the next lecture. Thank you.